So today we will discuss about rotational spectra of a diatomic molecule. So this is the simplest case because as we increase the number of atoms, it becomes complex and it is not easy to get the this exact spectral distribution, and we use most of the approximations at that time. But we will start with the simplest case and we'll discuss only this diatomic molecule throughout our this discussion. There are then another approximations which we will use. One is that we will treat diatomic molecule as a rigid rotor. Number second is that it will be treated as a non-rigid rotor. For this, what we will do actually, there will be called as the term centrifugal distortion. When we discuss with this, we will understand what it means actually, centrifugal distortion, because if you have a rotating body which is rotating at very fast speeds, so at particular time or instant of time, you will see that those two ends will be seen vibrating. That is because of the centrifugal force which will attract it towards the center, and at that time it will not be a rigid actually. So that we will discuss later on, separate case. So to start with the rigid rotor, we know that rigid rotor means it is a rotating body but it is rigid. Rigid means we are using an approximation that the two atoms of the diatomic molecule, let us suppose this is 1, this is 2, having mass m1 and m2, such that m1 is not equal to m2, and they are separated by some distance r. So with respect to each other here, and we also know that there is then a center of mass. So because this m2 is here, if we see that from the figure, you can say that m2 is greater than m1, so there will be a center of mass which will be close to this here towards m2. Let it be C. Okay, center of mass, and we are assuming it is a rigid, so the distance between m1 and m2 is fixed. It is not varying during the rotation or during any time whenever we are going to discuss this. So we are not assuming that r is varying. Okay, so r is a constant. And this is important point when you solve the rigid rotor actually. So we suppose that this molecule is rotating about the center of mass, where there is an axis which is perpendicular to the center of mass. So it's rotating about this axis, and it has an angular velocity omega. It has an angular velocity omega. Okay, now remember that when we are talking about the rotation of a molecule, there is a important parameter which is called moment of inertia. We have momentum in case of a linear motion, but here it is a rotational motion, so we have moment about the axis of the rotation. That is called a moment of inertia. And any body, if you take a rigid body, you have studied in your 11th or 11th class mostly, and then in the BSc classes, that for any rigid body we define three axes mutually perpendicular axes of, those are called as principles, axes of moments of inertia. So and every rigid body has three principal moments of inertia, one about each axis, and those are called as IA, IB, and IC. So what are those? I will tell you. These are different three axes actually, and they have been named as IA, IB, and IC simply. So molecules, any molecule, whether it is a diatomic, it is a triatomic, it is a linear, it is a non-linear molecule, these molecules are classified into groups actually. Classified into groups according to the relative values of their three principal moments of inertia. Okay, now the first one is I will quickly define these few basic concepts. Linear molecule. So linear molecule, according to name, you can see that all the atoms are arranged in a straight line. For example, HCl. Okay, like hydrogen chloride. Carbon oxysulfide, that is OCS. This is carbon oxysulfide. Okay, these are some of the examples of linear molecules. The three directions of rotations in any of these two molecules, there are more examples to this list, but I am mentioning these two which you will find easily. So the rotations, the axes of rotations, we are assuming there are three actually in these, because three directions which are passing through the center of mass of a molecule. Those three directions of rotations, if this is an HCl molecule, let me write it as like this. HCl is bigger as compared to hydrogen due to its atomic size, and we can take simply these three axes. Okay, now remember that this axis let this be give us IA, IB, IC. Okay, for example, these are just the principal. I'm not now these are same as actually coordinate axes, but here we are representing them as the moments of inertia, the principal moments of inertia. The directions are principal moments of inertia in this case. This IA is actually the axis along the bonds, okay, internuclear axis actually, about the bond axis. So this is simply the bond axis. This axis, it is perpendicular to the bond axis, and when a molecule will rotate about this axis, it will be rotating on the plane of paper, into the plane of paper, or out of the plane of the paper, any of these two. So it is just like that. I am placing something on this plane of paper and it is rotating like this, or it is rotating like this. So into the plane of paper, and there is an axis which is perpendicular to it. Okay, one. So let us assume that it is IB. So when a molecule rotates, so there are three different directions of rotations. One be the about the bond axis. The another one is called as, let us suppose this is and over and rotations in the plane of paper, or this in the plane of board. Actually on the plane of board it is rotating, so that means it is going like this and this is coming like this into the plane of paper. Okay, so here it is actually 2D surface. So just you can take it like this, that you are placing a pen on it on your notebook and just rotating it by two fingers, that pen. So that will be the plane on the plane of paper actually. Another one is this. If you see this axis is nothing. This is and over and rotations at right angles to the plane of paper. Okay, because when you take the plane of paper, so you have molecule HCl. So this is simple. I will not draw the axis. This is a simple molecule, for example. So this molecule can, you take it this, take it down. So just rotate it plane of paper, or take it into the plane of paper and take the perpendicular to the plane of paper. That means this molecule going towards perpendicular in the upward direction, this molecule going downward direction into the paper. So in both the cases, it is plane of paper, it is perpendicular to the plane of paper. So these are the three types of rotationers which can be observed in this molecule, in any normal molecule, in any molecule, in these molecules. Okay. Now, how to differentiate these linear molecules and other molecules? So the difference is in their moment of inertia, relative values of moment of inertia about the three different axes. And in this case, if you see the simple HCl molecule, this is H, let this be Cl. Okay, HCl molecule. So if you see this, so it may rotate actually. These two, this, it may rotate like this whole molecule. Okay, so it may rotate like this, and I will write HCl. It may rotate about its bond axis. So you have just like you, how can I say you? I hope you will understand it. That you have two atoms. You are rotating just about the bond axis, about the axis of the bond. Number one. So this moment of inertia, IA, is approximately taken to be 0. I will tell you why. Just wait a minute. Because there is actually the symmetric, it is all symmetric about these axes, this bond axis. There is no change in any parameter. It almost remains the same. Now for IB and IC, IB means in the plane of paper, you rotate it on the plane of paper. That means your H moves like this and CL goes like this. Number one, in that perpendicular, your H will move in the upward direction, or C will move in the upward direction, CL, or CL will move in the downward direction, H will move in the upward direction. Okay, so these two cases are actually same. for this linear molecule. Because in any case, we are changing the positions of H and Cl. It doesn't matter that if you are going into the plane of paper or you are going at perpendicular to the plane of paper, because plane of paper doesn't make any difference to it. It is just for the sake of representation or the difference between the two different types of rotations. Okay, so the molecule actually behaves same in its properties, and we can say that IB is equal to IC. In this case, when it rotates in the plane of paper, end over end rotation, it is end over end. So one end moves here, it comes here. So at one time, these two ends will cross each other. So it is end over end rotation actually. So in both the cases, because there is nothing additional with respect to H, with respect to Cl, everything is same. Only the way of rotation is different. So that will not change its any property. It's electric, magnetic, or any type of absorption or emission. Actually, that IA, which we take approximately, it is small. So that is why it is an approximately equal to, we took it 0. So for a linear molecule, IA is approximately 0 and IB is equal to IC. Then we have another one, which is called as symmetric top or symmetric top molecule. The example is methyl fluoride, that is CH3F, and the arrangement of the atoms in this molecule is C, F, H, H, H. Let's keep aside a bond axis, see the end over end rotationals. So the end over end rotationals actually this and this. Assume in the case of HCl, the same thing happens here, whether you go perpendicular to the plane of paper or about the plane of, in the plane of paper or out of the plane of paper. On the plane of paper actually, that's on the plane of paper and perpendicular to the plane of paper. So the behavior is same, there's no change, because a molecule in whole actually this rotates. Okay, so that means in this case again IB will be equal to IC. Now what happens to about the bond axis? Because in the linear case we have seen that it is almost approximately, it's almost 0. There's no actually, there's a very small magnitude of moment of inertia about that axis, because everything is uniform about that. But here the axis is CF bond, this bond axis. This is the main rotational axis, because if you see the center of mass or the center of gravity, that will be lying along this axis, and it involves actually rotation of this axis, carbon fluoride bond axis. It involves the rotation of 3 comparatively, that means which are not equal, massive hydrogen atoms of this axis as compared to this fluorine. So there is a, these are almost, these hydrogen atoms are equal, but here there is a difference. Here there is a difference in the masses. So there is a, that means about this axis the moment of inertia cannot now be zero, because there's a definite, actually you can say the mass, because I is equal to mr square, how we define the moment of inertia. There's a variation in this mass, F, C, and H here. So in this case, IA is not taken to be zero for symmetric torque. So in general, we can write IB is equal to IC and not equal to IA. In some case, there are two more different cases for this. When IB is equal to IC and it is greater than IA, it is called as prolate symmetry. And if IB equal to IC less than IA, this is called as oblate. This. For this is the methyl fluoride in this case, and in this case there is an example, boron trichloride. The arrangement in this case is B, Cl, Cl, Cl. So this is symmetric top. Then there is another that's called a spherical top. So in spherical top, actually, all the moments of inertia are equal. Example is methane, CH4 and CH. In another case is a symmetric top, and in this case no one is equal to another. And majority of the substances belong to this category. For example, CH2 double bond CHCl or water is an asymmetric top. Now these are different types of molecules based on their classification based on the moment of inertia. And now we will discuss actually our main topic, which is the rotational spectra diatomic molecule. So to rotate a molecule, we need a definite amount of energy. And in atoms, we have seen that there's electronic energy levels. These energy levels actually are nothing but they are representation actually that atom makes a transition when an electron jumps from one lower energy to higher energy or from higher to lower. This is a transition, dipole transition. And those energy levels actually are quantized. Similarly, in case of molecules, here we have molecular energy levels, and the transitions between these levels occur as they occur in the electronic energy levels. In the case of atom, the atoms, all forms of molecular energy, like in atoms, they are quantized. Like in atoms, with the energy levels are quantized. In molecules, the energy levels are quantized as well. So there is nothing like arbitrary amount of rotational energy or vibrational energy or any of these two or both of them. So there is a definite quantized value of any energy level. So the molecular energies are also quantized energy levels. So using this concept, the permitted energy values in these molecules, those will be rotational energy levels or the vibrational energy levels. And we will see that what is the spacing between the two vibrational or the rotational energy levels, and what is the how does the selection rule follow in these cases. Okay, so we will start from the simplest case, which I have already told you, and we have used one approximation that the molecule is rigid, where there is no change in the internuclear distances between two atoms of a diatomic molecule. Another thing is that when there is an increase in the number of atoms, there are the very broad approximations are used, and we will not use them here right now, and we will consider a simplest case. So the figure is same, which I have earlier plotted here. This one I will draw it again. Diatomic molecule. Let us suppose that we have M1, M2, and M1, M2. There is a internuclear axis. Since it's a two-body problem, so we will use the reduced mass notation because there are different masses, and there is a center of mass. So let this be the internuclear axis. Or the bond axis by which they are connected with each other. Okay, and there is a center of mass which will be somewhere close to this. Let us suppose it is here, because it is obviously I can say that if M1 is greater than M2, then it will lie close to this, and let this be the C center of mass, and from this center of mass it is R1, this is R2. Okay, let this be R0, equilibrium position. So this is the diagram which we will use. And let us suppose this, I will draw this an axis, moment of inertia axis, about which the molecule rotates end-over-end rotations. We are assuming that IB is equal to IC in this linear molecule. It is a linear diatomic molecule. IB will be equal to IC and IA is equal to 0. And for end-over-end rotations, this is the moment principal axis of moment of inertia about which it rotates. From here, we can clearly write that R0 is equal to R1 plus R2. And if there are end-over-end rotations about point C, this is C here. The center of gravity, then the moment of inertia is defined by M1 R1 will be equal to M2 R2. This is the equation for the balancing of the two masses about the center of gravity. Now, if you know that I is equal to mr square, and in this case let it be equal to, it is equal to m1 r1 square plus m2 r2 square. About the center of mass, this is the moment of inertia, about center of mass C is mr square, and is m1 r1 square plus m2 r2 square. Or I can write it as m1 instead of r1, here, get from here, I am writing r1 square, so you can calculate r1 square from here, r1 from here, so it is m1 upon, sorry, m2 upon m1 r2 square. Okay, so when we put up this value here, it is the first, second, third, so use second here in this case, so it is r2 from this equation. If anybody has any confusion, he can let me know. I can write it like this. Also, we know that m2 r2 is equal to m2 r2 will be r0 minus r1 from this, r0 minus r1, that is r2, or simply from this equation 1 here. So it gives us r1 is equal to m2 r0 divided by m1 plus m2, and r2 will be equal to m1 r0 divided by m1 plus m2. Is it okay? Because this r1 and this r1 here, it is taken out common here. Similarly, for the case of r2, you can derive the equation like this, and I can write then I is equal to, put up the values of r1 and r2 here. Let this be 4 and this is 5. Use 5 and 4, so use, so I will be equal to m1 m2 divided by, so when we use fifth in 4 here I, that means we are simply putting up values of r1 r2, r1 here and r2 here, and you will find that it is equal to r0 square, and I will write it as mu or not, so where mu is equal to m1 m2. You have all done this, actually there was no need to do it, and it's called the reduced mass of the diatomic molecule. Okay, so this equation, actually this, let's it be sixth, it defines actually the moment of inertia of diatomic molecule in terms of the bond length or not. Okay, now this was one step. In the second step, you already know that there is a angular momentum associated with a molecule in an atom, in a single atom. And similarly, there is an angular momentum which is associated with the molecule, and this is rotational angular momentum. So that rotational angular momentum, like in the case of orbital angular momentum in case of atom, here we have a rotational angular momentum is denoted by J. The energy of a molecule which is rotating about this axis, about any axis, will be called as rotational energy. A rotating molecule has rotational energy is not the only source of energy. There are other energies as well, but we are mainly concerned with the rotational energy. It will be denoted by E rotational, and it will have a rotational angular momentum J, such that E is equal to, this is for the case of a rotating molecule, I omega square, where I omega is J angular momentum, omega is the rotational frequency, this angular velocity, omega is the angular velocity, I is the moment of inertia. So these are all the basic things which are there, but there is a way to derive this actually. So J, so I can write it as J square by 2I. It gives is equal to E rotational. If you simply use that, E is that P square by 2M. P is the linear momentum. Here we have the rotational angular momentum, and use the M. There is a mu, or you have 1/2 of mv square, the kinetic energy. So here we have a rotational energy actually. Okay. So using those concepts and simple definitions, you can find out that E rotational is J square by 2, where J is the rotational angular momentum, and this J is like we have in an atomic physics case in an atom, like we have in molecule, because this is the angular momentum and it is quantized according to Bohr's theory. If you, which we use that the angular momentum is quantized and h cut. Similarly, this rotational angular momentum is also quantized, and it is given by this under root of J into J plus 1, and it gives us J square is equal to J into J plus 1 h cut square. So I can write here E rotational is equal to J into J plus 1 h cut square divided by 2I, and it can be written as J into J plus 1 h square divided by 8 pi square I, and it is an energy, so its unit is joule. While J is a quantum number, it is called a rotational quantum number, and it takes the integral values. So J is a rotational quantum number. Now, if somebody wants to solve it and get the derivation of this, I will remind you that just solve the hydrogen atom in polar coordinates. Simple. You have solved it. This is the rigid rotor, solution to rigid rotor. You can find it here. So these are the different. Now this is the complete treatment of this. I will send you this. So this is the polar coordinate equation. Because r is fixed, so the r coordinates will be del by del r is 0 and r is fixed. So everywhere you find del by del r in the Schrodinger equation for a hydrogen atom or simply for a two body produced mass problem, then it will be 0 r. So this r is fixed here. So del by del r everywhere, this term will go to 0. This part whole in general, this is 0 because r is fixed. And here it is solved, rigid rotor. So there is minus h cut square. This all is there here in it complete. This is given. So you have the phi equation. Solution of phi equation is a minus im phi. Then there is a m, and if you remember that, this is the legendary equation. This beta here is L into L plus 1. So we have E equal to h cut square by 2i L into L plus 1. So in the case of rigid rotor, we use J instead of L here. So this is how quantum mechanically it is derived actually. So there is in examination, there is no need to write it, but in case you want to understand it properly, you can use this derivation. Give me 5 to 10 minutes more, I will finish it. Okay. So the rotational energy, E rotation, is equal to h square divided by 8 pi square I j into j plus 1 in terms of joules, or you can convert it in electron volts as well. H is Planck's constant. You all know these notations. And j is a rotational quantum number. It takes integral values. But in case of spectra, when you study rotational spectra, what we draw actually, we draw the change in the wave number, nu. That is delta E by H. Nu bar Hc delta E, or frequency, that is nu simply, that is E by H, that is shift because of the rotation of the molecule. This is wave number, lambda inverse E by Hc. Hc by lambda, Hc by E is lambda actually. So lambda inverse is delta E by Hc. And this is the wave number. So this is frequency. E is equal to H nu simply from this equation. This is in terms of centimeter inverse units, and this is hertz. So because of the rotation, how much energy is absorbed or emitted, that will be determined from these equations. And the energies are represented as sometimes this nu bar, sorry, energies, not nu bar. So Ej, the energy corresponding to a particular value of J. J is a particular value of the rotational energy level actually. J will represent the energy level now here, because those are quantized now. So Ej is equal to Ej by Hc. So this is delta E, this is E. So there's a difference. And it is H. H is in the denominator. So instead of H square, it will be simply H. Centimeter inverse. And J is equal to 0, 1. I can also write it as B, J J plus 1 centimeter inverse, where B is equal to H by 8 by IC, and is called a rotational constant. Rotational constant. So I can draw the energy level diagram for this. So J equal to 0, J equal to 1, J equal to 2, J equal to 3, similarly 4, 5. As you go on, it increases actually. And to find the distance, this here. So this is EJ equal to 0. This is EJ equal to 1, EJ equal to 2, EJ equal to 3. Energy is like this. And if you want to find the difference, how much is this? How will you find? So the difference is for delta E, J equal to 0 to 1, difference between the energy level 1 and 0, that is J equal to 0 and J equal to 1, is equal to EJ equal to 1 minus EJ equal to 0. Now putting up these values in this equation, here in this, we know that EJ is equal to B, J into J plus 1. Now EJ equal to 1, so it is B into 1 plus 1, that is 2B. EJ equal to 0, put up the value here, 0, J equal to 0, it is 0. So what is delta E? It is simply 2B minus 0, that is 2B. So this separation from, if this is here, EJ, simply EJ E is equal to 0 for this case, and E is equal to 2B. So this separation becomes 2B. Similarly, you can calculate it for J equal to 1 to J equal to 2. So putting up the value first, J equal to 1 here, that is 2B, we know that. Now put the value J equal to 2. So it will be B into 2 plus 1. So it is 2B into 3, that is 6B. So that means this energy level occurs at 6B. What is the difference? 4B. Okay. Similarly, you can calculate, and this energy level occurs at 12B. So this is 6B. Similarly, this occurs at 20B, and this is 8B. So if you see, there's a trend now. That is, the trend is nu bar, or EJ simply equal to, you can term it in terms of ER, nu bar, wave number, and that is J to J plus 1 in general, from any J level to J plus 1. Is equal to so we have BJ, so that is B J into J plus 1. Wait, sorry. So we will write it as, it is B J plus 1 J plus 2 minus B J into, first I am taking J plus 1, this case here, minus the lower one, that is J simply. Okay, and if you solve it, it is B into J square plus 3J plus 2 minus J square plus J here, and it is 2B into J plus 1 centimeter inverse. Okay, so the distance is actually, the step 5 raises 2B, 4B, 6B, 8B. This is the increase when you change J by 1. And remember that the important thing is that the selection rule is delta J is plus minus 1. Important, this important. So we are not expecting any J equal to 0 to J equal to 2. We're only taking J equal to 0 to J equal to 1, J equal to 1 to J equal to 2, and similarly for others. Okay, so this is the selection rule. This is how the energy levels are calculated in case of the rotational spectra. The spacing between each level you can calculate, and the increment is 2b in between any two levels. First you have 0 to 2b is 2b, 0 to 0, then J equal to 1 to J equal to 2 is 4b, J equal to 2 to 3 is 6b. Okay, so this is how we calculate the spectra and all the energy levels. That is why I have drawn this spacing actually here. This increases. Okay, I think this is all for today. Let us see tomorrow further.